Swayam Prabha. Digital India. Educated India.
This is my multiple sinusoidal cycle that is available. I apply power for 2 cycles. I don't apply power for 1 cycle. Again, I apply power for 2 cycles. I don't apply power for the next cycle. What happens? If I try to look at the whole 10 or 15 cycles together, I would see that I am applying power only for 2/3 of the entire cycle, right? So obviously the net amount of power I am applying to my appliance gets decreased, right, if I try to do this. So what I am doing is applying power for integral number of cycles and not applying power again for integral number of cycles. So this is generally known as integral cycle control. We call this as phase control, whereas this as integral cycle control. So I apply power for n number of cycles. I don't apply power for m number of cycles for a total number of m plus n cycles. Right? So obviously I am going to definitely have no power transfer during this portion. So obviously I am going to have the net power that I am transferring is decreased as compared to what I had done originally, had I connected it directly to my circuit, rather than having this kind of a circuit in between. In this case, I would have fired it at 0 degree and 180 degree. So I would have fired for 2 cycles. 3rd cycle, I would not have given any firing signal. Then again, 4th and 5th cycle, I would have given firing signal. 6th cycle, I would not have given firing signal. Right? So this would also work, no doubt. This also decreases the amount of power that I am applying to my appliance. Only thing is, if the motor drive's inertia is very small, what you have generally as fan motors are hardly 40 watts consuming motor. Input is 40 watt and efficiency is pathetic, normally 30% or 40%. So what you get as the output is only 16 or 17 watts. So if you don't apply power for some time, बैठ जाएगा एकदम. It will not run. And again you apply power, it will start all over again. Again when you don't give power, it might just stop. Depending upon if you don't give power for 2-3 cycles in a row, एकदम बैठ जाएगा. That's it. So it depends upon what is the time constant of your system. If the time constant of your system is larger, then it may be able to pull along with the inertia. If the time constant of the system is smaller, integral cycle control is not good, because once again you have to start afresh, which is not good for the system. So typically integral cycle control is used in thermal systems. Let us say I have a immersion heater. Maybe I have some kind of heat convector. Please understand, thermal time constants are generally of the order of minutes or hours. It will take a long time to get heated up. It will take a long time to come down to cooling. So you switch it off for 2 cycles, it won't even feel it. Right? So in thermal systems, integral cycle control can be implemented. Whereas in motor drive systems, generally we don't use integral cycle control, rather we use phase control. So phase control is very commonly used in induction motor drive systems, be it single phase, be it 3-phase. Even in 3-phase, sometimes for starting the induction motor, you guys have done with auto transformer, starting in electromechanics lab. So instead of auto transformer, I can use this kind of a phase controlled SCR pair, back to back connected SCR pair, right? This is back to back connected, anti-parallel, right? So this kind of system can be used for slowly decreasing the firing angle. Rather, you will have 120 degrees or 110 degrees as the firing angle. Slowly bring it down towards 0 degree, so that you are applying slowly increasing voltages to your induction motor and it can pick up speed at a slow pace. That kind of starting mechanism is known as soft start. You are starting it slowly, softly, so you call that a soft start. So soft start is a mechanism which we use for three-phase induction motor with back-to-back connected thyristor in all the three phases. Of course, we will need in all the three phases, right? So this kind of a mechanism we may use for starting the induction motor in a slow fashion, which we call as soft start, right? So if I am talking about soft start, I have to show one phase, then second phase, and the third phase. All the three phases will be connected together like this, and then I may have one phase, second phase and third phase power supply. Let me call this as VAN, VBN and VCN, and then this is the three-phase induction motor. In fact, the back-to-back connected thyristor pair together is available in the form of a single device which is known as triac. This is available in the market. TRIAC, triac. So triac is available. One terminal will be called as M1, the other one terminal will be called as M2, main terminal 1, main terminal 2 and the gate terminal. So the gate terminal will be given pulses at alpha degree and 180 degree plus alpha, right? In both the times, the pulses have to be given so that the forward conducting device conducts during alpha degree time and 180 degree plus alpha, then the reverse conducting device will conduct. So we have single phase AC voltage controller, we have three phase AC voltage controller. We can have in either of them phase control or integral cycle control. So these are the different types that are available in the AC voltage controller. So if I take, for example, an AC voltage controller like this, please understand that if I can number it the same way like what we did. 1, 4, 3, 6, 5, 2. Please note I am numbering it the same way like what we did in the case of a rectifier. A phase positive device I am calling as 1, B phase positive device 3, C phase positive device 5 and the negative devices are correspondingly numbered 4, 6 and 2. Right? Now, if I am assuming that I am having the three-phase voltages somewhat like this. This is A phase, this is B phase, and this is C phase. Right? If I am having one of the phases conducting, the return has to be through the other one of the phases. Like if A is conducting in the forward direction, the return path has to be provided by either B or C. So one has to join hands either with 6 or with 2. Otherwise, I am not going to be able to have a continuous current. If I fire only one and nothing else is conducting, there is no way the current can flow. Right? The current has to flow through the other phase. So, if I look at normally a resistive kind of load. Let us say, forget about induction motor. If I have a resistive load, right? If I fire one here, for example, right? If 6 has to conduct along with that, the B phase voltage has to be negative. If it is not negative, I am not going to be able to have a current in the opposite sense because it is resistive. I am talking about a resistive load. So, I will have B phase actually, this is A, this is B and this is C. I will be able to see a current flowing in the opposite direction through the B phase only if at least VAB happens to be positive. Because please understand, the current is flowing from device number 1 and it has to return through B phase. So VAB has to be positive, only then I can have a current in that particular direction. So which means I can have the firing possible only until this point. I can delay the firing of A phase only until that particular point theoretically. This is a major difference between a rectifier and an AC voltage controller. In a rectifier we said alpha is first of all calculated with respect to VAC zero crossing, whereas here it is calculated with respect to its own phase voltage. The second point is, in rectifier we could go until alpha equal to 180 theoretically, whereas here we will be able to go only until 150. Alpha is 150. We cannot go beyond alpha equal to 150 for resistive loads. For inductive load it's different because inductance will have stored energy, it can continue the current for longer and so on and so forth. But for resistive loads I can have alpha ranges only from 0 degree to 150 degree for R loads. Is this clear? See, if I am saying that the current has to go from 1 and it has to return through B, 6. We are again following the same firing sequence, 1, 2, 3, 4, 5, 6. Again I will fire 1, 2, 3, 4, 5, 6 and so on. So I assume that 6 is already fired, it is up and running. Okay? If 6 is running, up and running, and 1 has to aid the conduction, then VAB has to be positive. Only then the current can flow from here and it has to return through this. So I am talking about VA coming here and VB coming here. Unless VAB is positive, I will not be able to have a current flow directly in the direction that I have shown, provided it is a resistive load. Right? If VAB has to be positive, VAB could be positive only until here. Beyond this, I am going to have basically B is increasing and A is decreasing. So VAB will become negative. So if VAB has to be positive, it can happen only until 150 degrees of the VA waveform point. If I try to look at VA waveform, it starts from 0 here and it is exactly 150 degrees here. So I can have a range of only, the delay could be only as high as 150 degrees. If I try to fire it beyond 150 degrees, device number 1, it will not have any chance to conduct because 6 and 1 combination cannot work beyond alpha equal to 150. That combination cannot work beyond alpha equal to 150. So two major differences between a 3-phase rectifier and a 3-phase AC voltage controller are, one is alpha is calculated always with respect to phase voltage zero crossing, not line voltage zero crossing. The second one is the maximum alpha that is permissible for resistive load conduction. If the conduction has to be feasible, in the rectifier case, theoretically, it could be 180 degrees, Whereas in the case of AC voltage controller, it has to be only 150 degrees. These are the major two differences between AC voltage controller and the rectifier that we discussed so far. Right? And firing, of course, is done symmetrically. If I say that 1 is fired at this point, obviously 2 will be fired at this point, and 3 will be fired here, and 4 will be fired here, and 5 and 6 will be fired respectively at these points. Symmetrical firing is generally done in this particular manner. Again, I have chosen alpha equal to 150. This is alpha equal to 150. Right? So alpha is calculated with respect to phase voltage 0 crossing. One last point before we move on further is that if I am taking a single phase AC voltage controller, for example, this is my voltage waveform, single phase AC voltage controller's input waveform, right? If I am going to look at this device being fired at alpha equal to 60. So obviously this device will be fired at 60 plus 180. So this will be fired at 240 degrees. Right? They are always shifted from each other by 180 degrees. Right? So this is my input and this is my load. Let me look at the current waveform along with voltage waveform. If I am looking at alpha equal to 60, that means I am firing somewhere here. This is where T1 is fired. And this is where T2 will be fired. Right? And if I am talking about RMS value for this with resistive load, it's pretty simple. Because I will have basically device number 1 conducting for this entire duration for R load and device number 2 conducting for this entire duration for R load again. So I should be able to write this as Vm sin omega t whole square RMS, right, d omega t. I have to go from alpha to pi and I have to average it over pi and square root. This is what is Vrms that I will be getting at the output. Right? This will be the RMS value at the output. So obviously I will have some cos alpha and so on and so forth. Or 1 minus 2 sin omega t by 2, whatever, right? You will sin 2 omega t by 2. That's what you will get as the expression, and then you have to integrate it, right? Sin square omega t, whatever. So this is going to be the output voltage as far as the resistive load is concerned. So it is not a simple expression like what we got in the case of rectifier. And this is in resistive load. If I look at inductive load, for the same thing if I try to draw for inductive load. So let me again draw the sinusoid, right? And I am firing it at alpha and again I am firing it at pi plus alpha. I will have the current rising from 0. In the other case, I would have had the current somewhat like this. The current would also have been something like this, right? For the resistive load, the current would have been something like this. Exactly the same wave shape as that of the voltage. Whereas, so this is the current waveform. This is I and this is V. Right? Whereas here, the current would have started like this. I have to write the equation again. Vm sin omega t equal to Ri plus L di by dt if I am taking a RL load. And then I have to again apply the same equation like what I did, where Vm sin omega t becomes equal to Ri. I will have the peak of the current and so on and so forth. All those things will be valid here as well. So I am going to have the current probably rise like this and then it will fall beyond pi. Please note this. The current is falling beyond pi. It will come down to 0. And again the current would have increased here and then it would have fallen beyond pi. This is how it is going to be. Right? Now if I draw the voltage is going to be somewhat like this. I am going to have the voltage, this entire thing coming up as the voltage until here. Get my point? So it is coming from alpha and it will go until beta. And solving for beta is not going to be easy again. Similarly, it will start from alpha plus pi and it will go until pi plus beta. So some portion of the positive voltage will also show up here and I will have this entire portion coming up. Right? If I have higher and higher inductance, this beta will get delayed further and further. You get my point? If I have higher and higher inductance, I'll have this beta delayed further and further. So at some point where I have a very large inductance, I may have beta almost reaching until pi plus alpha. Then I will have the full voltage applied. There is no way I'm going to have any control. So for highly inductive loads, I may not have any control almost until alpha reaches, even 60, 70, 80 degrees. I may not have any control over the voltage at all. So highly inductive loads, for lower values of alpha, I may not have any control over the voltage output and hence the current output as well. Right? So we'll continue with this in the next class to look at the limits of the control in an AC voltage controller. Right? By the way, AC voltage controllers is not given in NetMohan. So let me try to look at, because for want of a better book, I am trying to look for different books which will give you at least some amount of explanation for AC voltage controllers as well.